Hi students, today we are going to discuss about electronic configurations of elements and periodic table. So this uh, video is belong to unit 3 of chemistry class 11 and even for PUC students also. This video is a part 3 video. In the previous class we have studied about modern periodic table and modern periodic law. And this class we are going to talk about the electronic configuration of elements and the periodic table through examples, and even you can define electronic configuration in periods as well as group-wise electronic configuration. Friends, welcome to my channel. Myself is Vedamurthy. So this is one very important chapter for electronic periodic table. So in this today what we are going to study or discuss about the electronic configuration of elements across the periodic table. In the previous unit 2 structure of atom we have studied about the electronic configuration, but here we can learn the more in detail with the set of the 4 quantum numbers, that is K, L, M, N, and the principal quantum number even N. So this defines the main energy level known as shell. See students, we have also studied about the filling of the electrons into different subshells or referred to as orbitals, that is SPDF in an atom. So the distribution of the electrons into orbitals of an atom is called the electronic configuration. What is electronic configuration? The distribution of electrons into the orbitals of an atom is called electronic configuration. Elements allocations in the periodic table reflects the quantum numbers of the last orbital or field. In this section, we will also observe a direct connection between the electronic configuration of the elements and the long form of the periodic table. So, electronic configuration in the periods, the period indicates the value of n, means that is principal quantum number, for the outermost or valence shell. In other words, successive period in the periodic table is associated with the filling of the next higher principal energy level, that is n is equal to 1 and n is equal to 2, etc. So it can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that being filled. So the first period n is equal to 1. The first period n is equal to 1. So here the starts with the filling of the lowest level, that is lowest level is 1s. And therefore has two elements, hydrogen and helium. In the first period having two elements, that is hydrogen and helium. Okay students, so here in the lowest level one is having hydrogen and helium. So hydrogen electronic configuration we can write it as hydrogen electronic configuration is 1s1. Same way we can write for helium also. Helium, see helium electronic configuration is 1s2. When the first subshell K is completed, so in the first period, okay, and the second period where n is equal to, in the second period where n is equal to 2. So this starts with the lithium and the third electron enters to the 2s orbital. The third electron enters to the 2s orbital. Okay. So the next element beryllium has 4 electrons and has the electronic configuration is 1s2 2s2. So beryllium electronic configuration is 1s2 2s2. Beryllium electronic configuration is 1s2 2s2. So here, then starting from the next element boron, the 2p orbitals are filled with the electrons when sepal L is completed at the neon stage. So neon element. So starting from the here 2p orbitals are filling up in the say for example um, neon neon electronic configuration is 2s to 2p6. Here what will happen, the boron having the 2p orbitals, that is filled with the electrons when the L shell is completed. So in the at the neon ns 1s2 sorry 1s2 2s to 2p6. So thus there are 8 elements in the second period. In the second period, how many elements are there? In the second period there is 8 elements. 8 elements. So that is neon is the last one. So here neon is filling up with 1s2 2s2 and 2p6. Here the cell will, so L will complete. Okay. So the third period n is equal to 3. Third period is n is equal to 3. In the third period begins with sodium. Sorry, begins with the sodium. Third period is begins with sodium, and in the third period then added will enter the sodium again, will enter to 3s orbital. 3s orbital it will enter. So then successively filling of 3s and 3p orbitals gives rise to the third period. So third period also having total 8 elements from sodium to argon. Okay. The fourth period is n is equal to 4. So the fourth period will start from the potassium, and here the electrons will added and filling up the 4s orbital. 4s orbital will be filling in the fourth period. So now you may note that before the 4p orbital is filled, filling up 3d orbitals becomes energetically favorable, and we come across to the so-called 3d transition series. So this starts from the 3d transition series. Sorry, the 3d transition series will start from scandium. So its atomic number is 21. So which has the electronic configuration is so scandium electronic configuration is 3d1 and 4s2. 3d1 4s2. So here the third 3d orbitals are filled at zinc, where the value zinc is there 3d orbital is completely filling. So zinc atomic number is 30. So with the electronic configuration, zinc ends with the 3d 10 and 4s2. So the 3d orbital will be completing in the fourth period. So that is transition period. The fourth period also ends at the krypton with the filling up of 4p orbitals. The krypton will be having the electronic configuration which is completely filling up with the 4p orbitals. 4p orbitals. So next, so altogether, the fourth period ends with krypton, that is we know, sir, and altogether we have a total 18 elements in the fourth period. So 18 there are totally 18 elements in the fourth period. So first period is 2 elements. Okay, second is 8, and third period is 8, and fourth period is 18. Okay. The next will go for fifth period. The fifth period will the filling with, so n is equal to 5. So this beginning with the rubidium in similar to the fourth period and contains the 4D transition series starting at yttrium. So yttrium atomic number is 39. Yttrium atomic number is 39. Okay. So this period ends at the xenon with the filling up of the 5p orbitals. 5p orbitals will be filling in the fifth period. So that is ends with the xenon. The sixth period n is equal to 6. Sixth period is n is equal to 6. So sixth period contains total 32 elements. 32 elements, sixth period. Okay. And successive electrons enters into the 6s, 4s, 5d and 6p orbitals. So here in the sixth period will the electrons will be enter into 6s, 4f, 5d and 6p orbitals. So in the order of the filling up of the 4f orbitals begins with the cerium atomic number Z is equal to 58. So Z is atomic number, and that ends with the lutetium, that is atomic number 71. Lutetium is ends with the sixth period will ends with the lutetium, that is 71 atomic number. And to give the 4f inner transition series, which gives the 4f inner transition series, which is also called a lanthanide series. 4f inner transition series is, you can call it as lanthanide series. Next, the seventh period. Here n is equal to 7. Seventh period n is equal to 7, which is almost similar to the sixth period, and is successive filling up of the 7s, 5f, 6d and 7p orbitals. So, and includes most of the man-made radioactive elements. So in this period end with the atomic number 118. 118 will be the last atomic number in seventh period. So which also belong to the noble gas. So last seventh period belongs to the noble gas family. So this is seventh period is filling up of 5f orbitals. So that is actinium, that is equal to 89, which gives the 5f inner transition series that we can known as actinoid series. The 4f and 5f inner transition series of the elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Students, here we'll take one problem. How do you justify the presence of 18 elements in the fifth period of the periodic table? So how we can say that is 18 elements are there in the fifth period? Here very simple answer. So when that is, so n is equal to 5. N is equal to 5 in the fifth period. Here when n is equal to 5, L is equal to 0, 1, 2 and 3. Okay, when n is equal to 5, L is equal to 0, 1, 2 and 3. The order in which the energy of the available orbitals is, the energy of the available orbitals are 4d, 5s and 5p. Okay, so which increases just increase in 5s is less than 4d and 4d is less than 5p. So here the total number of orbitals are available as 9. So the maximum number of electrons that can be accommodated is 18 in 5 in 18. So therefore there are 18 elements are there in the fifth period. So next we'll know about the group-wise electronic configuration. In the group-wise electronic configurations, electrons in the same elements are allocated in the same vertical column or groups having the similar valence shell electronic configurations. The same number of electrons in the outer orbitals and similar properties. So for example, the group 1 elements, alkali metals, group 1 elements are alkali metals, all having ns1 electronic configuration, which is the valence shell electronic configuration that we can see in this table. Here atomic number is 3, so element is lithium and its symbol is lithium Li. So electronic configuration becomes 1s2 2s2 2s1, 1s2 and 2s1. So or even you can write it as helium bracket 2s1. So that we can write it as lithium like this. And another one, atomic number 11. So 11 belongs to sodium. Here the electronic configuration is 1s2 2s2 and 2p6 and 3s1. Even you can write it this in the simple form Ne into, that is Ne next 3s1. This is about sodium having the atomic number 11. Next, so next atomic number is 19, that is potassium. 19 is potassium. You can write the electronic configuration 1s2 2s2 2p6 3s2, okay, and 3s2, next remaining 3p6 4s1. So in the simple form we can also write like this: Ar argon 3s1, 4s1. So same way here we can see the another few examples, that is rubidium, cesium, francium. So all will get here the electronic configuration. So thus it can be seen in this properties of an element have the periodic dependence upon its atomic number, not on relative atomic mass. I hope students this unit or this part is understood. Thanks for watching the video.